You think the universe is familiar just because you exist inside it. But what if every assumption you hold is only a fragile surface? Is reality continuous, or is it made of pixels? If the universe expanded in the blink of an eye, did that moment really happen? If matter began massless, how did being come to exist? If most of your mass is empty space, then who are you? If half the universe disappeared, why are we still here? As billions of particles pass through us, why do we feel nothing? Did all diversity emerge from only 3 elements? If the first light of the universe still falls upon us, has the past truly passed? Are galaxies just magnified forms of quantum fluctuations? If the constants of nature were even slightly different, would the universe cease to exist? Is the universe single, or are we just one of infinite possibilities? These questions are not ornaments for curiosity. They are fractures in the surface of what we call reality. And by following them, we may arrive at answers that rewrite everything we think we know. Is reality continuous or made of pixels? Imagine a moment shorter than a trillionth of a trillionth of a trillionth of a second. So short that even trying to describe it in words feels like writing poetry, because the human mind cannot truly grasp it. That is the Planck era, the instant when the universe first drew breath. Time, space, energy, matter, everything we know emerged within that unimaginably brief interval. And perhaps the deepest mystery lies not in how the universe began, but in what form it took when it did. Is reality truly like a flowing river, or is it more like a screen built from invisible pixels? The Planck era lasted for roughly 10 to the minus 44 seconds after the Big Bang. When physics attempts to probe intervals shorter than that, our established theories fail. Just as you cannot zoom forever into a digital image, the universe appears to impose its own resolution limit. This limit may be the smallest pixel of reality. Hence, one of the most provocative questions of modern physics: is the universe continuous, or is it a cosmic display made of tiny, hidden pixels? Consider a film. Motion appears seamless to your eyes, yet it is nothing more than a series of still frames, on the order of a few dozen images each second, with your brain filling in the gaps. Could time function in an analogous way? Perhaps the now you experience is simply a succession of discrete Planck moments. What we perceive as continuity might be the universe's own cinematic illusion. This idea is not new. Various theoretical approaches propose that space-time is quantized, that it has a discrete structure. If so, the fundamental building blocks of reality are not atoms, nor protons, nor even quarks. Instead, the most basic bricks would be units of space and units of time, space pixels and time pixels. During the Planck era, the 4 fundamental interactions, gravity, electromagnetism, the strong nuclear interaction, and the weak nuclear interaction, had not yet separated. They functioned as a single, unified interaction. In a metaphorical sense, it was the instant when the universe spoke one language. As the cosmos expanded and cooled, that unity fractured, and the complex laws we measure today emerged. Hidden within that symmetry breaking is the central riddle. Why does reality present itself as continuous? Physicists are divided. Some argue that space-time is truly smooth, divisible, without limit. Others contend that it is composed of minimal units, like pixels. Advocates of the second view often point to the holographic principle, the notion that our 3-dimensional world is a projection of information encoded on a lower dimensional boundary. Just as a 3-dimensional video game ultimately consists of pixels driven by an underlying program, our universe could be the manifestation of a deeper informational substrate. If the universe is pixelated at the most fundamental scale, then consciousness must be built from those pixels as well. Memory, emotion, and identity would arise from the sequencing of unimaginably brief, discrete instants, like shadows flickering between the frames of the universe's own film reel. The I you experience could be an emergent pattern riding atop those basic informational units. Empirical clues are sought in the cosmic microwave background, the faint afterglow from roughly 13.8 billion years ago. It offers an image of the young universe, yet even this record cannot reveal the Planck era directly. At such early times, the universe was so hot and dense that photons scattered incessantly and could not travel freely. We will never observe the very first instance head-on. At best, we infer them from subtle imprints and indirect signatures. Why does this question resonate so powerfully? Because it reaches beyond physics into philosophy. If the universe is pixelated, what becomes of free will? Are our choices genuinely open, or are they patterns unfolding within a pre-written cosmic code? If time is a sequence of frames, is the present a fundamental feature of reality, or an artifact of perception stitching discrete instants into a seamless flow? There is another perspective. We are a species attempting to understand the universe's own birth. In doing so, the universe has generated within itself observers capable of reflecting upon its origin. The Planck era marks not only the limits of our instruments, but also the horizon of our concepts. It stands like a wall at the edge of knowledge, and perhaps, in a deep sense, the universe will never permit us a direct view beyond it. Yet this very obstruction drives discovery. Humanity progresses by pressing against boundaries. The Planck era may be the ultimate challenge, an invitation to develop a successful theory of quantum gravity, whether through string theory, loop quantum gravity, or an idea yet unimagined. We may one day derive testable predictions that distinguish a continuous spacetime from a discrete, pixelated one. So ask yourself, if we were to learn conclusively whether reality is continuous or pixelated, what would that mean for us? In a continuous universe, perhaps agency is fundamental. In a pixelated universe, perhaps agency is emergent, real at our scale, yet ultimately grounded in deeper informational rules. This debate reminds us of a crucial truth. The universe is not only external, it is also internal. We are the universe examining itself, and the Planck era marks the furthest edge of that self-examination. That instant, lasting on the order of 10 to the minus 44 seconds, remains one of humanity's greatest enigmas. Perhaps the deepest truth is this: we may never fully know, but in striving to know, in asking precise questions and following their consequences, we enact what is most human about us. If the universe grew in the blink of an eye, did that moment really happen? It is said that the universe expanded by 1 trillion-fold in the time it takes to blink. But did that blink really occur? If you say yes, then you must explain how time itself was born with that explosion, and whether an instant could be defined within the nothingness of what came before. If you say no, then where do you place the strong evidence we see in the sky, the fluctuations in the cosmic microwave background, the filamentary distribution of galaxies, all of them magnified and frozen imprints of that blink? Perhaps the most honest answer is this: it both did and did not happen, and even that statement is not enough. Those who say it did happen have clear grounds. The theory of inflation tells us that immediately after the Big Bang, the universe expanded exponentially. A region the width of a strand of hair ballooned almost instantly to the scale of the observable universe. This brief but violent period solves 3 great cosmological riddles. Why are the farthest regions of the cosmos the same temperature? Why is space so flat? Why are expected relics, like magnetic monopoles, missing? Inflation explains these puzzles. The force behind it was a field called the inflaton, trapped in a high-energy state and then released. The subsequent reheating filled the universe with particles. The tiny ripples in the cosmic microwave background we observe today are the magnified remnants of quantum fluctuations from that time. Galaxies, clusters, the cosmic web, all are echoes of that blink. The evidence is strong, thus the yes answer holds. But if you emphasize the word moment, then the door to know opens. At scales smaller than the Planck time, the laws of physics as we know them collapse. A moment only makes sense when there is a shared framework of measurement. Yet at the edge of inflation lies the possibility that time itself unfolded with the universe. If time began then, the so-called moment is not a marker within a flow, but the birth of the flow itself. Asking if it happened is like asking if a photograph existed before the shutter opened. The event that opens the shutter makes the photograph possible, and asking how long it lasted already presupposes the tool of measurement. To say no in this sense means what you call a moment here is not even definable. A third possibility arises. It both did and did not happen. This may sound contradictory, but the history of logic shows us that we can think beyond the binary of true or false. In open futures, some propositions may be neither true nor false. Some frameworks even allow that a statement can be both true and false without collapsing into absurdity. Applied to the inflationary instant, this means physical observations say yes, while theoretical and metaphysical reflections on time's nature say no. Holding both at once is not abandoning science. It is recognizing that different uses of the word moment are being conflated. The deeper issue is this: what do we mean by exist? A hill is only a hill because it rises from a plane. An object is only an object against a background. Without a background, the object cannot be. Some philosophers therefore argue that reality depends on nothingness. Objects appear upon it. From this angle, the question sharpens. Did the blink itself create its own background, or did it fold into an already existing flow? If time's ground was laid down with inflation, then that moment was not an event within existence, but the very threshold that made existence possible. The doorway is both the entrance and the room. To step inside is to create the room itself. Here we strike the limits of language. We speak of moments, events, before and after, but perhaps the very pavement those words walk upon was not yet laid. To say unsayable is not to silence inquiry, but to halt the insistence on the wrong category. Like an artist sketching background lines and then lifting the brush, the absence preserves the painting. With inflation, it is the same. Whatever we say is either too little or too much. Saying it did happen points to physical traces. Saying it did not happen probes the grammar of time. Saying it both did and did not broadens the scope of logic. Yet beyond all of these remains a threshold that words cannot cross. From this, 3 lessons for everyday thinking emerge. First, we must stretch the notion of a moment. To ask, how long did inflation last, is to pose a stopwatch question on the very track where measurement itself is being built. Theories may assign durations as internal parameters, but it is equally valid to ask how duration gains meaning in that scene. Second, we must not confuse evidence with concept. The statistical patterns of the cosmic microwave background and the distribution of galaxies speak in favor of yes, but they do not guarantee that the moment is the same kind of moment we use in daily life. Evidence belongs to the parameters of theory. Concept depends on the questions we ask. Third, we must not shut down thought in the face of contradiction. To say both yes and no is not babble. It may simply mean we are describing the same occurrence in different language games, one in the language of physical laws, the other in the logic of time. A contradiction is not always a mistake. Sometimes it is the marker of a threshold. So what does it mean for something to have really happened? If it means leaving an imprint, then yes, it happened, for the architecture of the cosmos bears its stamp. If it means occupying a stretch of time, then no, it did not, for the ruler of time itself was being drawn at that very instant. If it means being describable as a coherent chapter in a narrative, then both. It happened and did not, because different narratives yield different truth values. If it means being captured fully in language, then it is unsayable, because words falter at the threshold that sets their own stage. The coexistence of all these answers marks a rare crossroads between modern cosmology and contemporary logic. On one side, the mathematics of inflation, the magnified quantum ripples, the reheating flood of particles. On the other, the distinction between being and nothingness. For an object to appear, a background must exist, But if the background itself is born with the event, then the word event must be placed in quotation marks. Logic, in turn, opens another stage, suspending the rule of either or and showing that sometimes both, and tells the story more faithfully. And above all, there is the friction of language against its own silent boundary. To name the threshold diminishes it. To leave it unnamed hides it. Both are incomplete, both necessary. What resonates is not a simple answer, but the felt depth within a simple question. Can a blink write the future of everything? Yes, because its ripples sketched the galaxies and your body alike. No, because that blink also created the very conditions for blinking. Both yes and no, because being and counting belong to different games of speech, and beyond them all, there remains a quiet threshold where words fall short. Perhaps the most honest reply is as unassuming as the neutrinos that stream silently through your body every second. You do not feel them, yet their presence is undeniable. The moment of inflation is the same. It left its trace. We read the trace. And as we do, the very word moment crumbles in our hands. That crumbling is not a loss, but the maturity the question demands. For sometimes the truest question is not, did it really happen? But how was the ground for asking this question itself established? The answer lies there, in that blink. It both happened and did not happen. And to say so is not enough. Yet there may be no other way to say it. If matter began massless, how did being come to be? Masslessness sounds like nothingness, doesn't it? Yet in the earliest moments of the universe, masslessness was not an empty void, but the purest state of potential. Particles existed, fields existed, energies existed. Only at that stage, none of the particles had any weight. The actors were already on the stage, but none of them had yet put on their costumes. Those costumes arrived later, when the Higgs field entered the scene and clothed the particles, in that instant being took on form. This was one of the most critical turning points in the history of the cosmos, for the birth of mass enabled not just physical objects, but also bonds, relationships, chemical processes, and ultimately, life itself. Mass is not merely a property that allows matter to exist, it is the glue that gives the universe continuity and coherence. Immediately after the birth of the universe, conditions were so extreme that they are nearly impossible for us to imagine today. The energy density was so high that familiar particles had not yet emerged in distinct form. Instead, everything existed as vibrating fields. In such conditions, the laws of nature as we know them did not operate in their usual ways. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified under one single interaction. As the universe expanded and cooled, this unity fractured. The forces separated, not chaotically, but as part of a deeper order. In particular, the separation of the electromagnetic force and the weak nuclear force, known as the electro-weak era, was directly tied to the origin of mass. To imagine the electro-weak era, think of a stage where the actors, particles, are already present, but they are ghostly, transparent, able to pass through one another. The electron existed, but it lacked the stabilizing weight to pin it down. Quarks existed, but without mass, they could not bind tightly together. The whole universe flowed like a flood of light that could not form lasting bonds. Being was there, but without shape. Matter existed, in some sense, but without mass. It could not hold itself together. As the universe cooled, this symmetry broke. The electro-weak force separated into the electromagnetic force and the weak nuclear force, changing the laws of the cosmos forever. Electromagnetism became the basis for the bonds that hold electrons in orbit around nuclei. The weak nuclear force governed the radioactive processes inside atomic nuclei. Without this separation, neither atoms nor chemistry as we know them could have existed. And at this pivotal moment, the Higgs field entered the stage. The Higgs field can be pictured as an invisible energy ocean filling all of space. At first, particles moved through it without any resistance. But as the universe cooled, the field condensed and began to interact with the particles. Some particles slowed down, as if dragged through a thick medium, acquiring mass in the process. Mass was not an inherent property of the particles. It was the outcome of their interaction with this field. That is why what we call matter today is in fact the product of a hidden relationship. Certain particles, like photons, felt nothing from this ocean and remained massless, forever traveling at the speed of light. But electrons and quarks became heavy, and in that moment, being ceased to be pure potential and became structured existence. Without the Higgs field, the universe would be utterly different. Atoms could not form because electrons would not settle into orbits. Stars could not ignite because protons and neutrons would not bind. Planets could not exist, molecules could not take shape, and even the simplest forms of life would be impossible. The universe would remain a rushing sea of massless particles moving at light speed. In that world, being would never take the form we know. Thus, the mass conferred by the Higgs field is not just a physical trait, it is the very permanence of existence itself. But there is something even more striking. The value of mass is not a fixed law of nature. Had the Higgs field condensed with slightly different strength, the fate of the universe would have changed entirely. If stronger, particles would be too heavy to bond. If weaker, they could not hold together at all. The existence of the universe rests on a knife edge of balance. Our being is the fragile consequence of that fine tuning. So, how did being arise if matter began massless? The answer is that being always existed, only at first in an invisible, untouchable form. When the Higgs field spread across the cosmos, being acquired weight and permanence. It is like an actor waiting backstage without costume, present but undefined. Once dressed, the actor steps onto the stage as a character. Likewise, the universe first gained character the moment the Higgs field conferred mass. This perspective reshapes our understanding of existence. We usually think of matter as solid, permanent, unchanging. But matter is nothing more than a temporary trait bestowed by mass. Without the Higgs field, all form would dissolve into light. What we call reality is, in truth, a fleeting gift granted by an invisible field. Proposed in the 1960s and confirmed in 2012 at CERN through the discovery of the Higgs boson, this theory has become one of the greatest breakthroughs in science. It provided the first tangible answer to the question, why is there mass? Without this process in the early universe, neither stars, nor planets, nor ourselves would exist. In the end, we can say this: being did not emerge out of masslessness. Being was already there, only in a hidden, intangible form. When the Higgs field condensed, it clothed this unseen being in weight and permanence. At the end of the electroweak era, the universe transformed from a storm of light into a cosmos of matter. From then on, there were not just actors, but fully realized characters. We are living proof of that great transformation. The deepest secret of the universe may be this: what we call nothingness is in fact pure potential, and being began the very moment that potential put on its first costume, stepping onto the stage of time and space. If most of your mass comes from empty space, then who are you? If I told you that the combined mass of all the electrons in your body is about 21 grams, you might laugh first and then raise an eyebrow. But it's true. In a human of roughly 70 kilograms, all the electrons together weigh less than a small chocolate bar. And even that 21 grams exists only because of the interaction with the Higgs field. As electrons move through the Higgs field, an invisible presence filling every point of spacetime, they slow down, unable to race at the speed of light. That resistance is what we call the mass of the electron. But here comes the surprise. Almost none of your mass comes from electrons. In fact, even the bare Higgs-given masses of the quarks inside protons and neutrons make up only a tiny fraction of the total. So, where does the rest come from? The answer sounds like a paradox. From the vacuum. Of course, this vacuum is not nothingness. Especially in the so-called quark epoch, Just microseconds after the Big Bang, space was like a boiling soup of quarks and gluons, zipping about at nearly light speed, colliding, separating, and recombining. As the universe cooled, the strong force locked in. Quarks could never again be seen alone. This rule is called color confinement, and it works like this. Any composite particle in nature must be colorless in terms of quantum color charge. You can achieve that either by pairing a quark with an antiquark to make a meson, or by binding three quarks of different colors to form a baryon, such as the proton. The usual textbook picture shows three marbles, quarks, tied with springs, gluons. But the reality is stranger. The gluon field is a foaming sea of fluctuations. Place a quark in it, and you distort the field around it, creating a narrow tube of energy, and flux tube. Pull two quarks apart, and the tube stretches, storing more and more energy. Eventually, the system snaps, not by letting go, but by creating a new quark-antiquark pair from the vacuum. That is why you can never isolate a single quark. The vacuum itself actively enforces the rules. So where does the mass of a proton come from? Not from adding up the Higgs masses of its three quarks. That gives you barely 1% of the whole. The rest is the energy of motion and interaction inside. Quarks racing chaotically, exchanging gluons, surrounded by short-lived C-quarks that pop in and out of existence. All this dynamism contributes energy, and energy, as Einstein taught, is equivalent to mass. Just as a cup of hot tea is ever so slightly heavier than the same cup cold, a proton's swirling internal energy makes up nearly all of its mass. And since your body is built of protons and neutrons, most of your mass comes from this hidden storm of quark-gluon activity. To picture it, imagine the beach. The sand dunes are like the gluon field's waves. Drop marbles, quarks, onto the sand, and narrow tracks open between them. Those are flux tubes. Arrange three quarks into a proton, and the tracks meet in a Y-shaped knot. That knot is where the vacuum's fluctuations are most suppressed, and where the system pays the cost in energy. Stretch the quarks apart, and the knot elongates until the vacuum itself spawns a new pair to keep the bonds intact. This endless game at microscopic scales is what we weigh as mass. During the first millionth of a second after the Big Bang, the universe was a quark-gluon plasma. As it cooled, confinement set in. Quarks could no longer roam free, and hadrons, protons, and neutrons were born. It was then that the bulk of your mass was locked in place. The Higgs field had already given quarks and electrons their bare mass, but the overwhelming share of your weight crystallized when the strong force captured quarks into nucleons. So when you ask, if most of my mass comes from empty space, who am I? The answer is this. You are a stable knot of interacting fields. Every proton in your body is three valence quarks held in a storm of gluons and fleeting quark-antiquark pairs. These knots link together in atomic nuclei. Electrons orbit them, held by electromagnetism. Atoms form molecules. Molecules build cells. Cells build tissues. Tissues create thought. At the base of this entire chain lies the restless vacuum of the strong interaction. The Higgs field is still essential. It gives electrons and quarks their minimal bare mass, setting the stage for atoms to exist. But the vast bulk of you is the condensed energy of the quantum vacuum, measured out as kilograms on a scale. Lattice quantum chromodynamics, a powerful computational method, now reproduces the proton's mass directly from first principles, showing that this is not a poetic metaphor, but a physical fact. The vacuum itself generates weight. So who are you? You are not simply matter in the everyday sense. You are the echo of invisible fields, the knots of energy in the quantum sea, the foam of the vacuum woven into stable patterns. What you call your body is the visible surface of an ocean of activity. You are, in the deepest sense, a shadow drawn on the fabric of the void, a shadow heavy enough to leave footprints, to breathe, to remember, to ask questions. And perhaps that is the most astonishing truth. What we call emptiness is what holds you up. If half the universe disappeared, why are we still here? The universe did not want you. It is not pleasant to hear, but physics says so. In the very first moments of the Big Bang, every particle was born with its twin opposite. Proton with antiproton, electron with positron, quark with antiquark. When these twins meet, they annihilate into light. Simple arithmetic, +1 and -1 equals 0. If nature had enforced perfect symmetry, the stage would have closed within the first fraction of a second. There would be no stars, no planets, no eyes reading these words. But the curtain did not fall. The play continued, and understanding why is one of the hardest questions in modern physics. As far as we know, the cosmic balance sheet was slightly rigged. The cosmic microwave background and the calculations of primordial nucleosynthesis tell us that in the early universe, the difference between matter and antimatter was on the order of 6 in a billion. That means for every billion antiprotons, there were a billion plus just a few extra protons. This absurdly small excess is the reason for everything you see. The hardest rocks, the most fragile cells. Without that surplus, there would be no existence. And what we call vacuum is not empty at all. Quantum mechanics tells us that even the deepest vacuum is restless. Virtual particle pairs appear and vanish constantly. Bring two metal plates very close together, and you can measure the push and pull of these fluctuations. But this bubbling is fair. It creates and destroys in equal amounts. It cannot, by itself, tip the scales in favor of matter. Some other mechanism must have broken the tie. This is where Andrei Sakharov entered, laying out 3 conditions. First, the universe had to be out of equilibrium. That much is obvious. The expansion and cooling after the Big Bang was pure disequilibrium. Second, matter and antimatter had to behave slightly differently. Nature provides this, at least partly, through the weak interaction. In the decays of kaons, B mesons, and D mesons, the probabilities for matter and antimatter do not exactly match. The third condition was the most radical. The number of baryons, protons, and neutrons must not be strictly conserved. If it were, no excess could ever persist. If processes that violated baryon number did occur, their traces might still be detectable today. The CP violations we observe in the lab are real, but too small. The difference measured is not enough to explain why matter won. This is not a crisis, but an invitation to discovery. Either there is some hidden subtlety in the known processes, or new particles and forces remain to be found. The Standard Model explains a vast amount with stunning precision, but that very strength highlights where it falls short. That is why eyes turn to the neutrino, ghostly particles passing through us by the trillions, almost never interacting. We know they oscillate between 3 flavors, but do anti-neutrinos oscillate in exactly the same way? If not, even a tiny difference could have tipped the scales in the early universe. To find out, scientists bury giant detectors under mountains, ice, and deserts, hoping to catch the faintest flash of light from a neutrino interaction. Early hints suggest a difference, but the evidence is not yet conclusive. Another possibility is that neutrinos are their own antiparticles. If true, then a special nuclear process, double beta decay without neutrinos, could occur. Experiments deep underground, using lead, xenon, or tellurium, are watching for this ultra-rare signal. Detecting it even once would show directly how the cosmic balance tilted. We can make antimatter in the lab and study it. Antihydrogen atoms are trapped, probed with lasers, their spectra compared to hydrogens. So far, they match perfectly. Antimatter falls downward in Earth's gravity, not upward. No hidden reversal there. These results are not as romantic as some had hoped, but they are still progress. They show us nature as it is, not as we imagine. Cosmology also places limits. If large regions of antimatter existed, their collisions with matter at the boundaries would flood the sky with gamma rays. The sky is quiet. The cosmic microwave background is nearly perfect. The large-scale distribution of galaxies can be described with a single small parameter. All this suggests that a delicate, precise mechanism worked at the very beginning. Not a hammer, but a screwdriver. And there should be another echo. Primordial gravitational waves. Ripples in the fabric of space itself, frozen from those earliest instants. Already we hear the mergers of black holes. One day we may detect the baby universe's first cries. If those ripples carry the mark of broken symmetry, the mystery will end. Turn now to the human side of this question. The poetry of existence lies in a simple sentence. You are here because the universe is unfair. This unfairness is not a moral flaw, but a physical fact. You know symmetry can be beautiful, yet sometimes nature draws its beauty from imperfection. The vein in marble, the bubble in glass, the roughness in a voice. The cosmos sang through such a crack. If absolute symmetry had reigned, no ears would exist to hear the song. The numbers behind this story are not dry. We measure the universe's age in billions of years. The ratio of baryons to photons is a few parts in a billion. CP violation in kaons and B mesons, neutrino mixing angles, all whisper the same truth. Symmetry broke just a little. That tiny break endured, amplified, and became galaxies, stars, and brains. What comes next? More sensitive neutrino experiments, watching for that 2-electron signature of neutrino-less double beta decay. More powerful colliders, resolving the Higgs field more sharply. Telescopes probing the microwave background in finer detail. Gravitational wave detectors listening for the infant universe's hidden rhythm. Each of these may reveal where the crack in symmetry first appeared. And here is the most provocative line: you are not a mistake, but a child of a flaw. That does not diminish you, it enlarges you. Because flaws are where new orders are born. Life is not an accident of broken symmetry, but its natural outcome. Existence does not mean surviving in spite of the rules, but flourishing in the fissures within them. If half the universe disappeared, the half that remained was enough. That tiny margin carried the story. The leftover became matter. The story became you. So perhaps the question is not, why are we here? But how was it ever possible for us not to be? Once symmetry broke, a self-reinforcing cosmos began. Hydrogen clouds collapsed, stars burned, heavy elements formed, planets cooled, oceans filled, carbon chains coiled, neurons fired. Each step was the delayed consequence of that small imbalance. Trace the chain backward and you stop at one place, the moment symmetry broke. Physics seeks to capture that moment with numbers. Philosophy seeks to weigh its meaning. Your task is to take both seriously, because your very being depends on it. The final word should be clear. I said the universe did not want you. A better phrasing is, the universe did not plan you, but it made you possible. What made you possible was the tiny skew within perfect laws. Without the skew, no story. With it, the story began. Now it is in your hands whether to lengthen or shorten that story. Science gives you the tools. Curiosity gives you the will. The rest is your body. 20-something elements answering a deviation billions of years old. That answer is consciousness. And consciousness is the universe noticing its own flaw. While billions of particles pass through you, why do you feel nothing? Throughout the day, you are riddled with holes billions of times, and you feel nothing. More than 10 billion neutrinos per second pass through every square centimeter of your palm, emerging from the core of the sun, from the depths of the earth, from distant explosions, even from an ancient flood left over from the very first second of the universe. The root of this invisible crowd reaches back to the neutrino epoch, that fleeting period right after the Big Bang, when neutrinos decoupled from interactions before light itself was free to roam. In that instant, they largely loosened their ties to the universe, and ever since they have flowed on, cooling and thinning. Even now they are present everywhere, in every membrane, in every void, yet they drift through us, as if walking across the surface of a deep sleep. Why do we feel nothing? Because the neutrino is the particle that arrived latest at nature's bargaining table of the four forces and signed the fewest agreements there. It carries no electric charge, therefore it does not converse with light nor get tangled in the electron clouds of atoms. It has mass, but so small that the pull of gravity on it is negligible on everyday scales. That leaves only one door truly open, the weak interaction. We call it weak, and this is no courtesy but the naked truth. The chance of a neutrino colliding with any atom in your body and leaving a noticeable trace is so tiny that a popular analogy comes close enough. To stop a typical neutrino halfway, you would need a curtain of lead 1 light-year thick. In short, you don't feel them not because they ignore you, but because physics grants them an almost absolute right-of-way. To understand the history of this right-of-way, we rewind the cosmic chronometer. Less than a second after the Big Bang, when the temperature fell from trillions of degrees to more moderate values, the collision rate of neutrinos dropped and they decoupled from the tightly bound flow of matter. That window is the neutrino epoch. Photons would have to wait hundreds of thousands of years to travel freely, but neutrinos had already slipped away. Since that day, a sea of neutrinos, cooling as the universe expanded, has filled space. Today there are hundreds in every cubic centimeter, most sluggish as if in slow motion, some still racing fast. This fossil radiation's sibling to light is called the cosmic neutrino background. We have not yet detected it directly, but the traces it left, tiny but crucial tweaks in the early universe's energy balance, betray its presence. When we one day capture this background directly, we will have opened the oldest window into the universe's very first second. The primary source of our daily neutrino rain is the Sun. Fusion in its core, unlike photons, which may take eons to emerge, releases neutrinos almost instantly. Thus, neutrinos reaching Earth from the Sun report what happens in the core in real time. To catch them, gazing upward is not enough. We build giant aquariums underground. Hidden deep in mountains or buried kilometers under ice, detectors filled with pure or heavy water wait for years. They hope for the faintest ring of light from 1 in a billion collisions. When a neutrino strikes a particle in the water and nudges it near light speed, a bluish flash called Cherenkov radiation appears. Capturing it, we can say, it was here. Another approach wires endless ice with fiber optic eyes to catch the highest energy neutrinos racing through, messengers from active galactic nuclei, heralds of the most violent events in the sky. To say we saw them is more than a record of existence. It also reveals a secret. Neutrinos change identity en route. They come in 3 flavors: electron, muon, tau, and a neutrino born in one flavor can transform into another as it travels. This behavior, called oscillation, means only one thing: their masses cannot be zero. We do not know their exact values, but they are ghostly light, even compared to an electron. These small masses leave a subtle yet crucial brushstroke on cosmology's grand canvas. Being light and fast, neutrinos in the early universe tended to erase small-scale structures. From the distribution of galaxies and clusters, we can therefore place upper bounds on the total neutrino mass. The sharper we map the sky, the tighter we clamp that bound. Neutrinos speak not only in the heavens, but within the Earth. Born from the decays of radioactive elements, geoneutrinos seep upward into our detectors. Measuring them lets us estimate how much of Earth's inner heat comes from such decays, how the core and mantle balance their energy, all without drilling a hole. Thus we eavesdrop on the inner engine of our planet. When a nearby star explodes, neutrinos arrive before light. In 1987, neutrinos from a supernova were seen almost simultaneously in several experiments. It was the rawest, innermost information ever gleaned from a star's collapsing core. And since then, every nearby explosion keeps detectors on alert. But if they are so abundant and come from everywhere, why do we still feel nothing? Because our senses do not speak the neutrinos' language. The eye converses with photons, the ear with pressure waves, the skin with flows of heat. Neutrinos use none of these channels. Their only tongue is the weak interaction at the deepest core of atoms. The receivers for that tongue are not cell membranes, but mountains, not nerve endings, but kilotons of water. You don't feel them does not mean they don't exist. Like all things invisible at the wrong scale, neutrinos only become clear when measured at the right one. The neutrino's role in the future is as intriguing as its past. Why the universe is made almost entirely of us matter and not equally of antimatter remains a mystery. A tiny asymmetry, perhaps born very early among neutrinos, may have cascaded into the great imbalance that created everything we know. If so, neutrinos are not mere ghosts passing through us, but key actors in answering, why are we here? That is why some experiments seek to clarify their identity card. Are they identical to their own antiparticles? If so, under special conditions, a forbidden nuclear process, neutrinoless double beta decay, would occur, confirming it. For years, ultra-silent underground laboratories have searched for this signature. A single crack of light could illuminate the most critical margins of cosmic history. On another front, experiments attempt to measure neutrino mass directly. They weigh the tail end of tritium decay with microscopic patience, hoping to infer the neutrino's heft from the leftover energy. Even without knowing the particle's name, one can admire the elegance. You cannot stop the particle, but from the accounting of energy, you can deduce its body weight. And the final, perhaps most poetic goal, to capture the cosmic neutrino background directly. Ideas are on the table to make ultra-low energy relics bite into nuclei like tritium, producing a detectable trace. Difficult? Yes. Impossible? No. History shows many impossible feats became possible with the right scale and enough patience. All of this turns upside down the intuition we build around not feeling. Reality is not bounded by our sensory thresholds. A neutrino passing through your body does not touch your nerves, but it leaves fingerprints in the life-death cycles of stars, in the inner engine of planets, in the growth of galaxies. What sensation denies, statistics reveals. You may miss a single strike, but the collective effect of trillions can be captured. This is where science enters. By asking the right question and building the right net, the invisible suddenly becomes dazzlingly visible. Now return to the start and ask yourself, if you are unaware of something that touches you constantly, does that mean it has no effect? Neutrinos answer sharply. Their impact comes not in single blows, but in the statistics of an unignorable crowd. We look into the sun because neutrinos escaping it leave traces. We look into the Earth because geoneutrinos leak from it. We want to look into the universe's first second because the cosmic neutrino background still whispers, however faintly, everywhere. You do not feel them. That is how your biology is built. But you cannot afford to ignore them. Physics has long surpassed the silence of sensation. Perhaps it is time to stop calling neutrinos ghosts. They are not phantoms, but witnesses walking with hands in their pockets. They set out earlier than light, carrying the deep notes of stars. They pass through Earth, leaving the bill politely on the table. They quietly turn the pages of the cosmic history book. Just because you feel nothing today does not mean you will learn nothing tomorrow. The aftershocks of that first second still flow through us. We do not hear them, yet they keep speaking. And in the end, the question, why do we feel nothing, yields to a more honest one. How do we make the unheard visible? The answer lies in the patience of giant aquariums working day and night, in the cool eyes buried deep in the ice, in the statistics of the sky, and one day in the first direct signature of that ancient background. When that day comes, we will truly understand the age of those who change everything, despite being unfelt. Did all diversity really arise from just 3 elements? The universe began with 3 ingredients: hydrogen, helium, lithium. That was the menu. There was no carbon, no oxygen, no iron. So if you ask, did all this diversity really come from just 3 elements? The short answer is yes. But behind that, yes, stands a nuclear storm counted in seconds, a cooling that lasted hundreds of thousands of years, and star furnaces burning for billions of years. Right after the Big Bang, the universe was blindingly hot and dense. Protons and neutrons had only just begun to exist as distinct particles, and chaos was the only stable state. The first minutes were critical. As the universe expanded, the temperature dropped, particles slowed enough to catch one another and form small nuclei. Cosmologists call this brief window the nuclear minutes. During that time, here's what happened. Some neutrons locked onto protons to form deuterium as a temporary way station. This opened the road to helium, and at the very end, a tiny bit of lithium appeared. The most striking result of this chemistry was a simple ratio, about 75% hydrogen, 25% helium, and lithium only in trace amounts. The first variety was nothing more than 3 elements, but making nuclei was not enough. In that hot soup of the early universe, electrons could not yet settle around nuclei to form full atoms. That required another 300,000 years. At that point, electrons latched onto nuclei, light was released, and the universe became transparent. What we now call the cosmic microwave background is a frozen photograph of that moment. Fossil light whispering that the original ratios are correct. Up to this point, the story is plain. A beginning with 3 elements. But where did carbon, oxygen, calcium, iron, the rest of everything come from? The answer lies in the second great kitchen of the cosmos, the hearts of stars. Gravity pushes gas inward, pressure and temperature climb. As they climb, light nuclei fuse. Hydrogen becomes helium, releasing energy. That energy makes the star shine and counteracts collapse. A star is simply a nuclear engine balanced between gravity and radiation. Time passes, fuel runs out. In stars with enough mass, the temperature jumps up a notch. Helium in the core starts fusing into carbon. Still heavier stars become like an algebra notebook written in layers. Hydrogen outside, helium beneath, then carbon, neon, oxygen, silicon deeper in, a structure burning shell by shell like an onion. In each layer, heavier nuclei are born, until iron. Iron is a barrier. Fusing beyond it consumes energy instead of releasing it. The engine stalls. Once that barrier is reached, the finale is violent. The star can no longer resist its own collapsing mass. It caves in. In seconds, an unimaginable shockwave erupts. And at that instant, 2 things never before combined appear together: crazily high temperatures and a rainfall of neutrons. Nuclei scramble to grab neutrons. After the capture, the neutrons turn into protons, and the nuclei leap upward several steps in mass at once. This scene is a snapshot of the R process, the birthplace of most heavy elements: gold, platinum, iodine, uranium, all the desserts missing from the original menu. Sometimes this performance unfolds in a supernova, sometimes in the collision of 2 neutron stars. In 2017, detectors around the world caught the rippling of space-time itself. Telescopes saw a fireball at the same spot in the sky changing color over days as it faded. In the spectrum of that kilonova were fingerprints of heavy elements. In other words, the universe's hidden bakery was caught red-handed. So let's return to the question. Did all diversity arise from just 3 elements? Yes, the opening mixture was only 3: hydrogen, helium, lithium. But the richness of today's menu came from billions of years of processing in stars and explosions. The first 3 ingredients gave the raw dough. The recipes were written by stars, the oven was lit by gravity, and the final glaze was the neutron rain of cosmic detonations. Why didn't carbon or oxygen appear in those first minutes? Because the universe was expanding too fast. If you want nuclei to combine, you need time to hold them together. Even deuterium's survival required a narrow window. Helium could form only by rushing through before the window closed. That sprint, by its nature, left no chance for heavier nuclei. The universe ran a short nuclear sprint, then left the long marathon to the stars. How do we know the first mixture was really like this? 2 independent clues. The first is the cosmic microwave background, the photograph of universal temperature ripples at the moment of first transparency. The second is the helium abundance in very old gas clouds, regions showing the primordial mix before stars had time to pollute it. These two lines of evidence reinforce each other, making there were three elements at the beginning, not a slogan, but an observational result. Yes, lithium remains a small puzzle, but that is part of science's beauty. 95% of the picture understood, 5% still teasing curiosity. And the rest? Was it all stars? Largely, yes. Medium-sized stars like the Sun are masters of producing carbon, nitrogen, oxygen. Giant stars reach up to silicon and iron. The grand finale belongs to supernovae and neutron star mergers. That is why the iron in your blood comes from the heart of a long-dead star, the calcium in your teeth from a stellar explosion, and the gold in your ring likely from the collision of two neutron stars. The three primordial ingredients were the dough. Everything else came from this long process. What gives this story its viral punch? It begins with an unexpected simplicity. Start with three elements, build a universe. Then it rises scene by scene, minutes, hundreds of thousands of years, billions of years. The ratios fixed in those first minutes still show up in intergalactic gas. The light released at year 300,000 still drifts as static across millions of televisions. The crash of two neutron stars paints golden signatures across telescope images. And all those vast cosmic events connect back to the tiniest details. The oxygen in your breath, the hemoglobin in your blood, the silver-nickel alloy in a musician's instrument, the lithium in a battery. Now, rewind for a moment. If the initial mixture had been different, say far more helium and much less hydrogen, the lifetimes, formation, even the very existence of stars would have changed. If the universe had lingered longer during the nuclear minutes, lithium and beryllium might have been more abundant, but then the starting conditions for stellar chemistry would have been rewritten. So the three elements are not just a number, they are the calibration for the entire subsequent history of the universe. That we know this so clearly is the result of humanity's calm yet audacious observations, listening with radio antennas to the afterheat of the sky, examining the spectra of faint gas clouds silhouetted against distant quasars, measuring isotope ratios in nuclei struck by neutrons deep underground. We keep seeing the same signature, the weight of hydrogen, the imprint of helium, the faint whisper of lithium, a three-voiced chorus still heard after billions of years. So let us ask once more, with the wider view, did all diversity really arise from just three elements? At the beginning, yes, but that yes does not deny the rest of the universe. It makes it possible. The first mixture was the opening sentence of a cosmic story. Stars supplied the verb, explosions the object, galaxies over time the adjectives, and we now, not in one breath of course, are trying to read and understand that sentence. And the most beautiful part is this: the universe's menu today has dozens of lines, yet the kitchen remains open. New stars are still being born, old ones still dying, heavy elements still being rewritten in fresh explosions. The legacy of the first three ingredients diversifies a little more every second. If you like the thought, look at an object at hand, a fork, a ring, a grain of salt. Each one was cooked by a cosmic recipe. The first line of the recipe still reads the same: hydrogen, helium, lithium. The rest is the work of time. If the first light of the universe is still upon us, has the past truly passed? At night, when you look out the window, should I tell you that what you call darkness is in fact filled top to bottom with light? A light you cannot see, cannot touch, but that presses against your shoulders from every direction, like a hum left over from the birth of the universe, constant and insistent. Its name is the cosmic microwave background, the universal glow of the first photons released after the Big Bang, still raining down upon us today. So the question fixes itself here. If this first light is still upon us, has the past truly passed? The path to the answer began by chance. In 1964, two young astronomers in New Jersey, Arno Penzias and Robert Wilson, pointed an old communications antenna at the sky. The antenna was stuffed with pigeon nests and a white dielectric substance. Yes, the one you're guessing. They cleaned it out, polished it, and set it up again. Yet no matter what they did, the device kept picking up a microwave glow, equal in every direction. It did not change with day or night, summer or winter. Whether pointed at the Milky Way or at empty sky, the signal remained. They tried to dismiss it as antenna noise, but the signal was stubbornly there. Meanwhile, at Princeton, Robert Dicke and a young theorist named Jim Peebles were calculating that radiation from the early universe's extremely hot phase would have stretched into the microwave band today. As the universe expands, light's wavelength stretches too. A hot blue ember, receding, reddens. If the Big Bang were true, that fire's leftover light should now be cooled, spread evenly across all space. Penzias and Wilson's noise turned out to be the universe's baby picture, a background radiation at about 2.73 Kelvin, astonishingly smooth. How did this light come to be? In the universe's first 380,000 years, photons were not free. Everywhere was a dense plasma of protons and electrons. Light was scattered, absorbed, and rescattered at every step. As the universe expanded and cooled, protons were finally able to capture electrons. The first neutral atoms formed. With the plasma fog clearing, light was released for the first time and set out. Some of the photons emitted that day traveled for 13.8 billion years without hitting anything, and now drift through the room you're in. For us, that moment is long past. For the photons, it is still a journey. This glow covers the sky almost perfectly evenly. But that almost is crucial. The tiny ripples in the CMB's temperature are not at the level of 1 in 1,000, not 1 in 10,000, but 1 in 100,000. And those threadbare fluctuations seeded everything you see today. Galaxies, stars, planets, you. If the map had been perfectly smooth, the universe would have remained a thin soup forever. No structures would have condensed. Our existence is owed to the faint dominance of those little speckles in the sky. In 1992, the COBE satellite captured these fluctuations clearly for the first time. Then came WMAP and Planck. Sensitivity increased 100-fold, resolution many times over. We didn't just say, there is a light there. We measured that the light perfectly fits a blackbody spectrum, carrying a precise thermal signature. This alone was huge news. The early universe was indeed a hot soup in equilibrium, and as it cooled, its light shifted into microwaves. With Planck's sharper maps, we could calculate the universe's age, geometry, flatness, the ratios of ordinary matter, and dark energy. Out of a glow, we conducted a census of the cosmos. But how do these maps answer the question, has the past passed? Like this. In our lives, the past is like a page in a diary. You wrote it, it's closed. Not so for light. When you look at the sky, because the speed of light is finite, you are always seeing what has already happened. We see the moon with a 1-second delay, the sun with an 8-minute delay, the nearest big galaxy with a 2.5 million year delay, and the early universe with a delay of over 13 billion years. To see is always to be late. The record holder of this lateness is the CMB. We are looking at the universe in infancy, with baby teeth just sprouting. So then the past hasn't ended? It has, because that physical moment is gone. We cannot return to the plasma fog. But it also hasn't, because light from that moment still arrives now. Time flows in two different rhythms, the unfolding of events themselves and the arrival of their light to us. We live inside the second rhythm. In everyday speech, the past is like a draft thrown away. In the universe, it is converted into light and still in operation as a record. There is another instructive lesson in this record. The CMB tells us not only where we came from, but also when structures could begin to form. In the early universe, photons were so dense they exerted pressure on matter, delaying gravity's attempt to clump it together. After the universe became transparent, the photon pressure weakened. Matter could finally collapse and lay down the scaffolding of the first stars, then galaxies. So the light of the past is not just memory, it is the key to today's structure. The cosmic microwave backgrounds everywhere, every direction. Nature can sometimes create the illusion that it is a blanket draped afterward over everything. The opposite is true. This glow comes from within the universe itself. It persists even in the emptiest spaces between galaxies. It belongs to no galaxy in particular. It is the common language of the sky. That is why, no matter where you point your telescope, you hear the same melody. Only with very sensitive ears do you notice it is slightly sharper here, slightly flatter there. And from those tiny variations, science built a whole cosmology. What should all this make us feel? First, that what you call now is not as sealed a box as you think. We imagine the moment as a thin slice cut off from before and after. In truth, the now is a vast hall filled with light from events billions of years old. Every star you see is sending you a shard of its own past. The CMB is the widest, oldest mural of the past. You are walking through a rain of radiation streaming from what has already happened. Second, it shows why evidence feels so powerful. The CMB is not an idea, but a map. Its uniformity and its tiny ripples are not a theory's cosmetic overlay. They are measured reality. And the same light, observed by different instruments, always speaks the same mathematics. This is one of cosmology's rare luxuries. The universe has preserved the heat of its earliest moment and is still sending it to us. Third, cosmic humility. CMB photons are older than you and will outlast you. The atoms of your body were forged in stars, their journeys convoluted. The CMB photons, by contrast, come straight from the universe's infancy. Millions of them are in your room right now. You don't feel them, but they are upon you. Your temporal pace, birth, life, death, is but a spark compared to theirs. They set out long before you were born. They will still be traveling after you are gone. So what about a final judgment on that first question? Has the past truly passed? The scientific answer does not end in a single word. Yes, because that physical era, the plasma epoch, recombination, the first free photons, is irretrievable. No, because the radiation from that era still surrounds us, dripping into the present as data. And perhaps, most honestly, the past is still alive in the form of light. We understand today by looking inside that light. Now bring this to a personal scale. One night, past midnight, in a place where city lights have faded, lift your head. From every point your eyes can reach, something older than all visible things is raining down upon you like an invisible drizzle. The infancy of the universe still whispers to you in the quietest tone. It does not say, "I have not passed." It says, "I passed and became light. I remain here, inside your present." And you know the only way to hear it is by paying attention, because sometimes the oldest answers are spoken in the softest voice. Perhaps that is the point. In our languages, the past is a closed notebook. In the universe, it is an open file of light. As we turn the pages, photons continue to fall from that file. If the first glow is still upon us, the past both goes and stays, gone, so that cosmology is possible, present, so that cosmology is beautiful. Are galaxies just enlarged quantum fluctuations? If the universe were perfect, we wouldn't be here, because in a flawless universe, everything would have the same density. Gravity would give no region an advantage, no cloud would collapse, and no star would be born. Galaxies, the giant spirals, the massive ellipticals, the filaments that connect them, exist precisely because perfection is impossible, because emptiness can never be completely silent, because of the ground tremors of that stubborn uncertainty. we call quantum. Are galaxies just enlarged quantum fluctuations? Short answer, largely yes. Long answer, yes. But the word just trivializes the story. For those tiny quantum irregularities to become galaxies, three things had to act together. A very early expansion burst called inflation, the patient and ruthless amplifying power of gravity, and the complex behavior of matter, especially the invisible dark matter and gas. Let's start at the beginning. Beneath what we call particles, there are fields: the electron field, the quark fields, the neutrino field. These fields fill every point of space, and because of quantum, they can never be completely flat, completely silent. When we say vacuum, what we actually mean is background noise with the volume turned down, but never fully off. Normally, these fluctuations remain confined to the subatomic scale. In everyday life, we don't feel their effects. But in the first moments of the universe, there was a brief inflationary phase. Space expanded unimaginably fast in an immeasurably short time. In this cosmic blow-up machine, those tiny quantum jitters were stretched to vast scales. In technical mathematics, it's complex. Simply put, microscopic ripples were magnified to stamp themselves on the macroscopic world. Thus, the universe was saved from being a perfectly flat porridge. Some regions were a hair's breadth denser than others. Gravity did not dismiss this difference. Because gravity presses wherever it finds contrast, denser regions began to pull in matter from their surroundings. As the difference grew, the pull strengthened, like a vicious cycle, but in reverse. A small advantage turned into a great gain. Giant gas clouds formed. They collapsed inward. Stars ignited. Stars assembled galactic nuclei and disks. Behind today's cosmic web of filaments, voids, clusters, this was the driving force. But how do we know what shape came from quantum? Because the large-scale map of the universe still carries the statistical imprint of those first tremors. When you count galaxy positions, when you measure how often large voids, thin filaments, and dense knots repeat, you see that the first irregularities were seeded with an almost scale-independent pattern. More simply, there were similar bumps at both small and large scales. This is why both dwarf galaxies and giant clusters could emerge. Gravitational lensing maps, light bending around invisible mass, confirm the same picture. The luminous galaxies we see hang on a much larger invisible skeleton, dark matter halos. So the seeds came from quantum, the skeleton was built by dark matter, and the stars painted the visible surface. Here the word just hits a wall, because not every quantum seed becomes a galaxy. Gravity is the engine, but not the only actor. Gas must be able to cool, otherwise there is no collapsing fuel. In sufficiently heavy halos, gas heats up in collisions, then loses its heat by radiation and sinks inward. Star formation bursts at the center. But in very small halos, the blowback from stellar explosions, supernovae, can expel the gas again, drying up the structure. In very massive halos, jets and winds from giant black holes at the center reheat the gas, slowing excessive growth. That's why the sky hosts galaxies of every size, dwarfs, spirals, giant ellipticals. The quantum seed gave the starting condition. The outcome was written by the cooperation of environment feedback and dark matter topography. So why was inflation necessary? Because inflation locked in the quantum fluctuations on cosmic scales. Normally, the phase, direction, and timing of quantum ripples interfere and cancel, staying microscopic. Inflation pushed these ripples beyond the horizon, cutting them off from one another. Thus, the randomness from quantum effectively turned into classical density differences, map-markable bumps. Without inflation, the universe would have been much smoother, likely too smooth to build structure. This picture naturally explains three big phenomena we observe today. First, hierarchical growth. Small structures form first, then they merge and grow. N-body simulations, giant computer experiments, show this frame by frame. Dark matter points first grain, then link like a net, then knots swell. Galaxies and clusters settle in those knots. Second, cosmic web geometry. Gas flows along filaments feed galaxy growth. Voids expand, filaments thin, knots strengthen. Third, statistics. Distinct scales in the distribution of galaxy separations. For example, sound waves propagating through the plasma of the early universe, leaving rulers behind, tell us galaxies really did arise from wrinkles. All of this confirms the seed idea from multiple angles. Still, saying quantum fluctuation equals galaxy is incomplete because in between lie billions of years and a symphony of physics. The chemistry of gas changes. The first stars were very hot, very massive, and short-lived. They exploded and enriched their surroundings with heavy elements. These new elements, by opening cooling channels, allowed gas to cool more efficiently, triggering second and third generations of stars. Galactic disks rotated, producing bar structures. Bars drove gas inward. Central black holes fed. As black holes grew, they heated gas. Star formation was suppressed in some places. Meanwhile, galaxies merged. Mergers destroyed disks and created giant ellipticals. All of this was the network of roads from quantum bumps to galactic cities. Can order emerge from randomness? Yes, thanks to gravity. Think of randomly scattered grains of sand forming dunes with the wind. The starting points may be random, but the process generates definite patterns. The mathematics of the universe is generous here. Gravity makes dense places denser, empty places emptier. Moreover, it ties this to a threshold. Small tremors above a certain magnitude grow, those below fade. That threshold was enough to make quantum tremors into seeds. And the evidence? The statistics of the sky. Huge surveys measuring how galaxies cluster, mapped gravitational lenses, absorption marks left by gas in the distant universe. Different methods give the same picture. The universe is the enlarged form of the first wrinkles. As the picture grows, the model is tested. Simulations match observations, pixel by pixel. When they don't, they whisper hints of new physics. For example, small-scale tensions may carry clues about the micro properties of dark matter. Sometimes this objection arises. Quantum is random. How can complex structures like us result? Precisely for that reason. Quantum provides variety at the start. Gravity amplifies small differences. Gas physics and feedback choose the details. This trio doesn't make a deterministic recipe, but it does produce an inevitable statistical outcome: structure. So when we say galaxies are just enlarged quantum fluctuations, the word "just" should be read not as belittling, but as the first indispensable link of the chain. And there is also this, the place of humans in this story. It may sound poetic, but it's simply true. The first map of the atoms that make up your body was drawn in quantum uncertainty. That uncertainty was magnified in inflation, molded by gravity, cooked in stars, mixed in the arms of galaxies. Every light you see in the night sky today is proof that the vacuum was never completely silent. We are the amplified echo of the whisper of emptiness. So the conclusion? Yes, galaxies are, to a large extent, enlarged quantum fluctuations. But to make a Milky Way out of that seed, the universe had to play the whole orchestra. Inflation, gravity, dark matter, gas cooling and heating, stellar explosions, black hole winds, mergers. One wrinkle, one note, the symphony performed by physics. The spirit of perfection is boring. The universe works through small imperfections. And thank goodness it does, because in a perfect universe, there would be no stars, no city lights, and no one to watch them. What if the constants of nature were slightly different? Would the universe cease to exist? Would you believe me if I told you that the fate of a universe could be written on something as small as a sticky note? A note with only a single number on it. That number has already been chosen. Roughly 1 divided by 137. If you are breathing, thinking, reading these lines today, one of the reasons is this peculiar number. Now come, let us face this seemingly simple question. What if the constants of nature were slightly different? Would the universe cease to exist? Nature has certain numbers. We call them constants because in every measurement, in every equation, no matter where in the world you look, they remain the same, like the speed of light, like Planck's constant. But one stands apart from the others, the fine structure constant, alpha, which sets the strength of the electromagnetic interaction. What makes it special is not only its ubiquity. It carries no units, not meters, not seconds, not kilograms. It is pure ratio, like a word independent of the language of the universe. That is why, if they were to send only the number 137 as an intergalactic message with no explanation, a civilization searching for an intelligent source would recognize that this number is no coincidence. 137 is 137 to them as well. So what does this number tune? Think of it as the volume knob of electromagnetism. It sets the baseline probability that a photon will stick to, scatter from, or be absorbed by an electron. Turn the knob up, and electrons converse more strongly with light. Turn it down, and they whisper. The strength of this conversation sets the size of atoms, the stiffness of bonds, the richness of chemistry. If the knob is turned up too high, electrons cling more tightly around the nucleus, atoms shrink, and the flexible rearrangement of chemical bonds becomes harder. If it is turned down too far, electrons loosen. Atoms and molecules easily fall apart and cannot hold order. Even a few percentage points of change can dramatically reduce the likelihood of carbon being born in stellar furnaces. Without carbon, organic chemistry collapses. No complex molecules, no proteins, no DNA. Alpha acts like a dimensionless ruler that sets atomic scales, atomic radii, ionization energies, the fine splittings of spectral lines, all slide with its temperament. Shrink the atom slightly, and the same element becomes an entirely different chemistry. Even the periodic table's order would shift to another geometry. Sodium's willingness to give an electron, chlorine's eagerness to take one, carbon's ability to form 4 bonds and generate skeletons of molecules beyond imagination. None of this is an accident. If the knob of alpha is shifted, these patterns unravel. The shadow of this number affects not only chemistry, but also the lives of stars. How opaque stars are to photons, how energy is carried from core to surface, where the balance of pressure and temperature in the core is set, all depend on the subtleties of electromagnetic interaction. If alpha were larger, stellar interiors would be more opaque, energy more reluctant to escape. This could lock stars into dim, stubborn dwarves, or turn them into short-lived explosive giants, releasing pent-up energy. A smaller alpha would lower core pressures, shift the threshold of fusion, and prevent some stars from ever igniting. When the life schedules of stars change, the universal calendar changes. If stable light does not rain down on planetary surfaces for years, for billions of years, the clock of complex life cannot be wound. In the big picture, alpha's role becomes even more chilling. Before the bond between light and matter dissolved in the early universe, the critical temperature at which photons went free also depended on electromagnetic interaction. Had that moment come later or earlier, the growth of matter fluctuations into celestial bodies would have played out differently. In short, the seeds of galaxies and planets would either have scattered more sparsely or never taken root. One number changes, and the entire cosmic gardening plan is rewritten. Such fragility is unsettling. But why exactly this value? Why do we rest around 1 divided by 137 and not slide toward 0 or climb toward 1? An intriguing clue is this: alpha is not truly fixed, but changes slowly with energy. As the energy of collisions and interactions rises, the effective value of alpha grows. Just after the Big Bang, at insane energy levels, this knob was almost at maximum. As the universe cooled, the knob turned down and came to rest in the range we know today. Physics tells us about this trend, but not why the resting point is exactly here. Still, we can be grateful. If the knob had fallen to 0, there would be no electromagnetism at all. Not that atoms would collapse. Atoms would never have existed in the first place. Its lack of units makes alpha even more enigmatic. When you write down the speed of light, you must specify meters and seconds. When you declare the gravitational constant, you must explain kilograms, distance, and force. But alpha speaks the same language to everyone. This could be a sign of something hidden. Perhaps alpha is the outward trace of a deeper relationship among other constants. Each constant is a ratio converting quantities in different corners of the universe. Perhaps alpha is the ratio of ratios. Perhaps behind quantities like Planck's constant, the speed of light, and electric charge, there is one mathematical mechanism, and alpha is its naked signature. Yet another possibility, still fresh, lingers. The constants may have been chosen at the universe's beginning by a throw of dice. If countless universes exist, each born with different constants, then our finding ourselves in one that permits life ceases to be surprising. This is called the anthropic principle. Just because everyone walking along the Bosphorus sees a bridge does not mean there is a bridge everywhere. We too may simply have landed on a shore that happens to have one. The charm of this idea is clear, but the heart of science dislikes laziness. An explanation cannot settle for saying, otherwise we wouldn't be here. The question must be asked in reverse. Why do some numbers really behave as if they are linked? Why does alpha bring together so many ratios across different domains into one value? Here a small thought experiment comes to the rescue. Imagine you could send a tiny message into space, a very short number. What would you send? Not pi, because though you do not need units to measure a circle's circumference, you do need a shared contract in geometry. Not the speed of light, because meters and seconds would have to be explained. But 137 alone says something else. It may be the quietest way of saying, we are here, and we understand electromagnetism. This is a provocative hint that alpha may resemble a mathematical constant more than a physical one. Perhaps our mathematics is not yet deep enough. Perhaps we need a new language to glimpse its hidden face. Now let us return to the opening question. If the constants were slightly different, would the universe cease to exist? The answer must be spoken with care. The universe would not vanish entirely. Space-time would still exist, fields would still fluctuate, but the universe might not look like a universe. Stars might not burn, chemistry might not function, the rhythm inside atoms might play a different melody. Most importantly, observers would not be born. What disappears is not the universe itself, but the beings within it capable of telling stories. For us, nothingness is not the absence of existence, but a multiplicity in which no narrative can take hold. This fragility is also an opportunity, a number slipping into everything without units, hundreds of seemingly independent phenomena pointing to the same knob. This marks the right question. There is a goal harder, but more fruitful than measuring each fundamental number. Why do these values fit together this way? Why do they not only keep life possible, but hold everything, from the birth of stars to the breath of atoms, at the same setting? If one day we can give a deeper answer, perhaps we will discover a new law of nature. Perhaps the constants need not be constant, but are inevitable consequences of a theory. Perhaps alpha is simply a reflection of the invisible geometry of the universe. When that day comes, 137 will not be remembered as just a number to be erased from a note, but as the first letter of a great story. For now, here is what we have. If the fine structure constant had been even a little different, atoms, as we know them, would have been either too frozen to ignite or too fragile to hold together. Stellar furnaces would have either stayed dim or burned out too quickly. The delicate balance of carbon, oxygen, and water would have been lost. On planetary surfaces, seasons would never have unfolded. Life's time would not have been enough. Its chemistry would not have clicked. Our universe is not a silent stage set without spectators like us. It is a finely tuned music that has managed to reach the stage. Unsurprisingly, the tempo of this music is held by a single number. Some see this delicacy as a dream of coincidences, others as the trace of a deeper necessity. Whichever path you take, the question retains the same vitality. Is the fate of a universe placed in the lap of a number? Perhaps the answer is this: it was never placed. That number was the summary of a greater story. We pinned it to the wall and pondered it for years. And as we thought, we realized this. Sometimes, to understand a universe, You do not need giant telescopes. You need to understand a number small enough to fit in your pocket. And that number still speaks. In every atomic line, in every chemical bond, in every wave of light, with the same whisper, I decide what you are, but why I am this way. That is for you to find. Is the universe single, or are we just one of infinite possibilities? When we look at the sky, we see less than we think, because the speed of light sets a limit. Everything our eyes can reach lies within a sphere drawn by photons that have managed to arrive to us. Beyond it is not darkness, only invisibility. As far as we know, the universe heated up and began expanding about 14 billion years ago. It is still expanding. This simple fact opens two possibilities. The universe may be very large but finite, or it may truly be infinite. Both strain the limits of reason. First, let us draw the simple picture. The observable universe looks like a sphere with us at the center. This sphere is not a wall, but a marker of time. The farther we look, the deeper into the past we see, and at some point, there is no more past to see. Since expansion has continued throughout cosmic history, the farthest objects we can see today are about 45 billion light-years away. This means the boundary is not a line, but a limit carved into time itself. What lies beyond is unknowable directly. Yet geometry and physics offer us two powerful guides. A finite but edgeless universe is possible. Sometimes our reasoning traps us with false questions. If it is finite, it must have an edge, it seems. Then immediately follows, what is outside that edge? This trap arises when we forget how space can curve. Picture a small ant walking on the surface of an orange. The ant can walk in any direction and never hit a wall. Yet if it continues long enough, it returns to its starting point. The area of the peel is finite but without edges. Our space is not a surface but a three-dimensional volume, and yet it could bend back upon itself in a similar way. Mathematics calls this a three-dimensional sphere. Hard to visualize, simple to think. You go in a straight line, and after long ages, you return to where you began, just as the ant did on the orange. This idea is not only elegant, but measurable. If space curves back on itself, then very distant light rays would trace repeating paths, showing the same structure in multiple places in the sky, like a hall of mirrors. Such effects have been sought but not seen. Their absence is itself a clue. If the universe is curved back on itself, its curvature is so vast that to us it appears flat on cosmic scales. It must be at least 1,000 times larger than the observable region, perhaps 1 trillion times. Even then, we still speak of a single universe. There is no edge, no outside, only immensity. Another possible shape for a finite universe is different. Instead of an orange, imagine a donut, a ring with a tunnel through the middle. The three-dimensional counterpart of this space would allow shorter loops in some directions and longer in others. Light traveling one way might follow a long detour, in another direction, a short one. We could then see the same galaxy appear in different parts of the sky at different ages. That would be a measurable signature. Maps so far have shown no such signal. This does not erase the donut option entirely, but it requires the universe to be several times larger than the part we see. Again, we are speaking of a single universe. Again, no edges. Again, no outside. Now comes the unsettling possibility. What if space is truly infinite? Infinity is not merely a long road. It bends logic itself. The question, can the infinite grow, is already a puzzle. In an expanding universe, what grows is distance itself. The void between galaxies stretches. The stitches of an infinite fabric spread apart, yet remain infinite. Infinity does not forbid expansion. It only tests our patience. The most disturbing result of an infinite universe is the possibility of repetition. Nature's building blocks are limited. The kinds of fundamental particles and the ways to combine them are finite. If you write an infinitely long book with a finite alphabet, some sentences must repeat. The chance that a planet like ours, a city like ours, a room like ours, and even a copy of you reading these lines exists somewhere, is not zero. It may be vanishingly small, but infinity is large enough to sprinkle even near impossibilities across itself. The bad news: such copies are so far away that no physical contact is possible. The good news: here and now, our uniqueness remains intact. Even if repeated elsewhere, your moment is yours. There is yet another idea that complicates this picture. Infinity may lie not only within space, but also in the number of universes. Some theories propose that the universe went through a phase of rapid expansion in its early moments. Under certain conditions, this expansion never ends, but continues in some regions. Space would then inflate unevenly, forming separate bubbles. Each bubble would set its own laws in motion, mark its own cosmic calendar. We would inhabit one such bubble. We could never see our neighbors, because the expansion of the space between us builds an impassable wall. This vision is called the multiverse. The reason it is discussed in physics is that certain constants in our universe fall within narrow ranges that allow life. It looks like fine-tuning. If many bubbles exist, each with different values for the constants, then what is surprising is not that we are here, but that we must think about all those places where we are not. Is this an escape? Number. Without observation, a theory is only hope. The multiverse offers a mathematical logic we can share, but tying it to reality requires measurable signs. We cannot look beyond our horizon. Everywhere we can see is limited by the last daylight could reach us. Still, indirect clues may exist. Collisions between bubbles could leave marks, a vast circular scar across the sky. None has been seen. Moreover, measurements of cosmic curvature show the universe passes the flatness test with remarkable success. This does not prove a single universe, but it challenges the multiverse as well. Good science tests even its favorite ideas. An infinite universe stretches the picture, but it does not dictate destiny. Infinity does not guarantee that every possibility will occur. It only guarantees a place for every possibility. Whether that place is filled depends on the laws of physics. Without the right conditions for chemistry, the alphabet of life cannot be written. Our story is the outcome of long waiting and the alignment of the right sequence. That makes it unique. Yet on a wide enough stage, it may repeat. This seems like a contradiction. It is not. They are answers to different questions. Why are we here? Partly a local answer, partly a universal one. Even in a finite universe, the outcome is the same. In an edgeless space, if you travel far enough, you return to where you began. Companions on that journey lie within the observable universe. None are shadows of infinite multiplication. Yet we must not forget, edgeless does not mean ordinary. Even within the finite, the range of possibilities is vast. The number of galaxies overwhelms comprehension. The stars of a single galaxy outnumber all the grains of sand on Earth. In such immensity, is it more surprising that life arose only once, or that it took root in many places? We do not know the answer, but the question has the same power whether the universe is single or many. At times, the objection arises: if there are other universes, what good are they? If we can never reach them, what is the point? The point is not in how many places we can travel, but in how deeply we can understand the principles. An equation may explain an event before our eyes, and that explanation may open the door to new experiments. Without leaving, we can still speak of what lies beyond. Better telescopes sharpen the edges of our horizon. Better theories show which ideas lead to measurable results. Step by step, we move forward. Now let us return to the opening question. Is the universe single, or are we just one of infinite possibilities? There is no direct yes or no, but there is a carefully built because. Because everything we can observe allows both a finite without edges and an infinite expanse. Because geometry shows the possibility of boundaryless forms. Because physics says that expansion makes sense in both finite and infinite stages. Because method demands testable signs, and what we have seen so far has narrowed some possibilities while leaving others afloat. What can we trust? 3 things. First, the universe we see is, in a word, vast. Either it is the only stage, or it is one act in a colossal play. Both are breathtaking. Second, the window for life to emerge is narrow. We are here because that narrow window opened. This does not mean we are special, but it certainly does not mean we are ordinary. Third, we can go beyond knowing. We can keep testing. Doubt is the motor of science. Each new measurement scans the sky more finely. Each new result chips away at the edges of this great question. Could we one day find an indirect trace pointing to a multiverse? Perhaps. Or perhaps we will find clearer proof that the universe is vast, yet single. There is no guarantee of a final solution, but the road toward it teaches us this. The human mind, though finite, can ask infinite questions. Its reward is sometimes an answer, sometimes a better question. Final word. Whether we live in a single universe or just one of infinite possibilities, our task remains the same: to reach toward the horizon, to study the time and matter and laws hidden in the fading image there. Our share may seem larger than what we expected, yet it is worth it. For meaning lies not in competing with our doubles in other universes, but in asking the question here and now, with full measure. Single or many? The most honest answer we know today is this: with what we know, it could be either, and striving to know is more valuable than either.